All right, so welcome back, everybody. Today we get to start chapter 9. And it's been a while since we've done any concrete or abstract physics in here. But remember, once a week we'll go out there. I will have a ton more of those little nails that everybody needs Monday for when we go back out there. Cool. So within chapter 9, we are going to be looking at one big idea and kind of how it's applied. And we see this idea show up in a lot of places. Various places of physics. It shows up in chemistry, but the idea is essentially the same in whatever field we're looking at. So first off, if I gave you an option of getting hit by like a ping pong ball flying at 50 miles per hour or an equally sized, I don't know, ball of lead, which one would you rather get hit with? Why? It's lighter, okay, for sure, which means there's probably going to be less force that hits you, right? Okay. Now, as we're looking at that, I think I heard somebody say a magic M word in there. We are looking at two ideas. The big idea kind of running through this chapter is the concept of momentum, which we'll get a new Greek letter for, and its conservation. Now, when we talk about conservation, this idea shows up everywhere in the world of physics. It shows up in biology for a different meaning. Conservationists in biology are very different kind of approach. When you see the term conservation and you're thinking physics or possibly chemistry, what comes to mind? So chat it out, because I guarantee you guys have heard it, and you've probably seen it with like conservation of like 4 different things. I'm going to give you like 30 seconds to a minute. Talk with each other. Anything related to conservation that you've seen in a physics class. Here we are. Let's say that I have I'm gonna start a chemical reaction. I'm gonna light a fire, is what's gonna happen. And I'm gonna light my fire with one piece of wood. And hypothetically, there's a wonderful piece of wood that, let's say, has a mass of 1 kilogram. Okay, easy. When I burn this wood, I light it on fire, okay? I come back. What remains when I come back, an hour later? 2 hours later? Ash. That's it, right? Okay, how much does it weigh? You think it weighs a kilogram still? So I'm just going to make up a number. I didn't weigh this, but let's say I now have 0.3 kilograms. Okay, it feels as though I've broken a fundamental rule of the universe. And all of a sudden, what I'm hoping you guys start to recall is from physical science, this idea called the conservation of mass. Okay, we cannot lose stuff like this. Seemingly, we broke it. Did we really lose any of our mass? So it's not gone. It's not right there. Can you be more specific? Where is it? It's in the air. We had the rest of this stuff turn to soot, turn to smoke, turn to ash. It floats away, and we've lost a ton of it. Now, same thing. Wood, even if it's dried out, has a bunch of water in it. There's water vapor in it even when it's dry. It's gone. But it's not really gone. It's just separated from our idea. Now, a cool application of the conservation of mass in general. Back in the day, I don't remember the year, I'm guessing mid-1800s. They took somebody who was about to die, and they weighed them. Okay, boom. They weighed them, they died, and then they weighed them again, and they saw their weight was a little bit different. What do you think they concluded? Why? They lost their soul. Now, in reality, lost, I don't know if that's the right terminology, but pick your favorite flavor there. In reality, what do you think happened with that person's body? Gases start to go, right? You start to dry out if you're not replenishing. Cool. If we had this experiment run in a chamber where everything was enclosed and we weighed the whole chamber, burned it, and then weighed the whole chamber again, would we see a change? No. Now, with a little grain of salt, because a fancy guy called Einstein, some of that mass doesn't disappear, but it is changed directly into energy. Okay, so some of it leaves as light, which is a weird idea to think of how does it go between the forms, not our focus. But everything is conserved. The same amount of energy and mass that we started with is there when we end. Okay, that's a conservation of mass. Are there other things that are conserved that you have seen? Energy, cool. So similar idea, conservation of energy, conservation of mass, conservation of matter. Those are all things that you guys have seen in physical science. Shot in the dark, anything else you think is conserved maybe? Momentum is conserved. So with that, we have a little bit of a kind of jumping in point. Our first section is 9.1. And we are looking at two ideas which we'll define here soon. But we're going to look at impulse, is what it's called, and momentum. Okay. So we are starting to get into the category where we can think about collisions and things like that. So here's what we want to think about and what I want you to keep thinking about. If we have two objects colliding, there are very different things that happen as we watch it. Before they collide, we can measure their speed, their mass, all that stuff. They collide, and something happens during that collision, and then they change paths. Okay, there is a bunch of stuff going on here, and it's all related to these ideas. So this is redundant, and I hate it, but I'm going to sneak in definitions right off the bat. So impulse first. As we look at this, impulse does not have its own nice letter. Now, when I hear impulse, it makes me think of something that you just feel driven to do. Not the case with physics. It just happens to be the same word, different meaning. We are simply going to look at impulse. And we're going to think about this in a few different ways, but we'll just say it is the product. So we're multiplying something. It's what we get when we take the product of average mass, or average force, I'm sorry. So I'm going to go ahead and say force bar, or if you'd rather, F average. So some average force acting on something, times time, and time. Cool. That's it. Force and time will get you your impulse. Now, it has another meaning that we'll see soon, but while we're here, we need to talk about the momentum as well. So it looks weird in our notes, but if you're not opposed, I would, momentum, weird. I would rather just leave this big awkward gap and just have them both defined right next to each other. Okay, you guys have heard momentum. Who has more momentum walking down the hallway? Abigail or Tolly? Why? What if Abigail's walking twice as fast? A little harder to calculate, right? And that makes sense that it should be harder to calculate. Okay, you guys all have a basic understanding of momentum. How'd you describe it? Same thing. Wrong answers is probably what I'm expecting here, which is totally cool with. Chat it out. I'm going to call on one random person as soon as I find my calculator. What is momentum in your brain right now before we talk about it? You're going to see this and you're going to call it a P. I'm fine with that. It looks like a P. It is really the Greek letter rho, which if you do a P and just have it come forward like this, and mine doesn't really look that obnoxious normally, more like this. But this is the symbol that we're going to use for momentum. This is the Greek letter rho. Cool. Don't care if you know that it's called rho. You can just write a regular P. I'm fine with it. This is momentum. Okay. When we look at these things, turns out I like Angel's definition. This is simply the product of mass, which just remind me, mass M, what's our SI unit? So that's the label for it. We use M as a label. Kilograms. And what's a better word for speed? Because speed is as, yeah, go ahead. Velocity. Perfect. And velocity, which we would call V, what's its regular unit? Or SI unit? Meters per second. Awesome. Now, remember, speed and velocity is similar idea, like super similar. We just take absolute value. You can't have a negative speed. You can have a negative velocity. Cool. So we have these two ideas. Product of how fast you're going, and mass is what we call momentum. We have this idea of impulse, which is some force over time. Now, as we go through here, we're going to tie these two ideas together. And right off the bat, it doesn't happen very often here, but we get this wonderful thing that is always true. It can be proven to be true, called a theorem. Cool. We haven't seen many theorems in here, but we're going to go crazy. We get the impulse momentum theorem, because these two ideas are certainly related to one another, and we're going to clear up that relation in this theorem. Okay, THM is my shorthand for theorem. Man, we don't have many theorems like ever in pre-calc or here, which is unique for math and physics. Cool. All right, so it's been a long time since I've been in here. How do you find force? Isaac Newton might ask you. Love it. So I'm just going to start there. Recall, we have that force, F, is equal to mass times acceleration. This is a very particular rule. Whose rule is this? Or which law, rather? Love it. I think it was Rafa. I think. Newton's second law. Cool. Now, remember that we saw this interpreted a different way as the thought of torque as well. It's a different application of it, but we're not doing torque right now. Cool. All right, so we're just going to start doing some substitutions in here and see if we can't connect these two together. I have force, love it, and I have a mass, so these two seemingly will be related somehow. We just have to get there. Now, I'm going to do some annotations in red where I'll just make use of stuff. I have force and I have mass. What else do I need, though? If I'm looking at momentum specifically, mass and what? Velocity. Gosh, what's acceleration? And there's a lot of ways to answer that question. I'm going to scoot that over just a little bit. So, a bunch of different answers I can expect. And if we're morning time, so we better just commit here. Ooh, unless Angel's ready to go. All right, number one. What's acceleration? And who's number one? Love it. How fast my velocity changes over some interval of time. Okay. Everybody recall seeing this. Cool. Now, it's not our focus right now, but I do want to make sure they don't lose it. This is acceleration. Nice job, Alex. What's velocity? Good. Change in position is what I would call it, but distance over time. Yeah, I got it. Cool. All right. Can I use this acceleration equation here to plug in here? Let's do it. So, right off the bat, we get force equals mass times the acceleration, which we just found was change in velocity, delta V, over a change in time, delta T. Nothing crazy, right? We are just relating these ideas. Okay. Now, we are one step away from getting to our lovely impulse momentum theorem that we're going to make sense of. Anybody love fractions? Okay, so everybody loves fractions, that's obvious, but everybody would prefer to work without them. How do I bust this fraction? And you don't have to write this, but just so it looks a little bit clearer mathematically, I could write this expression like this. And if you don't love the fraction, you're going to multiply each side by something. Delta T. So I will show this, and I wish I could stay consistent with colors, but I just want to make sure that we show every little step along the way. Okay, they gone. Baller. Which I'm going to rearrange this just a skosh so it looks a little nicer. We get a force here times what? Good. So F delta T, or force times time. I'm fine with that. And over here we get mass times delta V, or velocity. Okay, check this out. As we look at this expression, notice the product of the force and time is impulse right here. This is my impulse. I can see it. Product of mass and velocity, M and V, check it out. Here's my momentum. Apparently, we have our impulse is mass times some change velocity. Everybody cool with that? Now, we're going to expand that idea. As time changes, momentum will change as well. But similarly, the impulse will change because those two things are related. So we're going to go just a little step further and just make sense of one little thing. I'm going to keep this right here, F delta T. And I will make that delta a little bit bigger just so it looks nicer. Okay, and really, really clearly, obnoxiously clear, one might say, I'm just going to make sure that we tie this idea to impulse. There it is. That is my impulse. Okay, let's deal with that right side, see if we can't do anything to make it look just a little bit nicer. I know that this is equal to M times delta V, and we are just using all these old ideas. How on earth would we expand delta V? Like, if I want to find a change in velocity, how do we do it? Say it again? So I'm going to use V, but I love it. VF, that's my what? Final velocity. And it's just the difference between my final velocity and my initial velocity. Okay. Is there any obvious algebra just begging to be done at this point? Okay, Riley says this. What is this? Distribute, right? Cool. So we'll go one step further, and then we'll have one last substitution. Looks like we're done. I could have MVF minus MVI if I distribute. Mass times the final velocity, and I just subtract mass times the initial velocity. Okay. I want to look again at that right side. We already decided that F delta T winds up being the impulse. That's just how we define it. What's the right side? MVF, mass times velocity. What did we call that a second ago? Not less, but momentum. Cool. All right. So here we go. Our big theorem coming together we're going to use the heck out of. MVF, this is just an ugly row, first of all. This is our final momentum minus my initial momentum. This is it. Okay. All of a sudden, we have a nicer way to think about the impulse and momentum and how they relate, or especially impulse. Momentum's easy. Mass times velocity. Abigail mentioned energy earlier. MV squared shows up with kinetic energy. So it makes sense that your mind was at energy here. We just don't square it. Okay. We have a new way then to think about this. Impulse right here, and this is the boiled down version of our theorem. Impulse is equal to, how would you explain what's happening here? Something F minus something I. It's a difference or a change in the momentum, right? Boom. Here we are. For this, impulse is simply a change in momentum. That's it. Okay. As we go through here, we're going to make a little tiny connection to some calculus stuff just to kind of front load so you can get to see some of these ideas. I'm going to find a couple things for us, and we're going to be calculating out a few impulses here, a few changes in momentum, just to see what we can get. So we're going to do an example, and we're going to calculate impulse. And we're going to do this in a nice way, I hope. Toli, what are you doing right now in calc? So are you doing integral from A to B yet? Okay. Do you know what this is doing when you do it? Love it. Okay. You're going to have a better time at this. Maybe. We're not going to get too crazy with it. Okay. So we're going to give us graphs. We're going to make sense of this with a lovely graph. So here we go. Let's say that I have, here's my positive x-axis. We'll just use things nice. And I have time down here, and we have a force applied on the y-axis. So we can measure it. Now, I'm just going to pick nice, easy numbers to deal with. How much time are we going to let this force act on something? Don't care what the number is. Shout it out. Ralph, what's your favorite prime number? Seven. Love it. Cool. We have 7 seconds. That happened.
What is phi?
Where do you see phi?
What is that? What that is?
This?
Yeah.
This is a rho.
Oh.
It looks like a P. That is our momentum. Yep. So I should have said, I'll just do delta momentum right here just to clear that up. Okay. All right. Huge challenge. I'm going to apply a force over the course of 7 seconds, and it's going to be nice and perfect. Let's say it's 20 newtons of force. I'm just going to put 20 right here. Okay, 20. Whoa, that was too big. 20 newtons. Okay, check it out. We're getting crazy. Let's say I apply a constant 20 newtons of force here, up until here. Now, if I want to find this idea, I think that we have a wonderful way to do it. I know that if you take force times time, you get the impulse, right? That's how we define it. What's the y-axis? Representative of force. and the y or the x-axis is representative of time. So if I said, hey, find me the area of that, you're finding me literally force times time, right? Find me the area here. I want you to express your impulse with the correct units. I know we haven't talked about units yet, but we're going to work them out here. How do you measure force? Newtons. And how do you measure time? Seconds. Cool. I want you guys to find me the momentum in Newton seconds. Sorry, the impulse in Newton seconds of this situation. I'm going to get two more for you. On B, I'm going to pause it so you don't have to do it. 20 times 7, I think, right? Just take the average force at 20. Cool. We take the times 7, and I get the impulse, or if I would rather, because we don't have a nice letter for it, I'm going to call it delta P. Cool. Or delta rho, if you will. And it's, you said 140? And what's the unit here? Newtons come in to newtons. Seconds come into seconds. 140 Newton seconds. Cool. Now, for this, whether or not that's a big change in momentum, we'll see here in a couple minutes. Nothing crazy, though. We just find the area. Okay. How about on this one? This is a much more complex shape because it's a triangle. How do you guys do this triangle, out of curiosity? Okay, so you do 30 times 10 divided by 2. I'm fine with that. You're using the actual 1/2 base times height. Cool. Alternatively, because we have the picture, without having to remember the formula, do you agree if I extended that I have a rectangle? And that rectangle's area is 600. Cool. That triangle is how much of the rectangle? You're right. Half. So I get the same number. 300. It's the exact same thing. I just want to make sure that we can see, isn't it? Am I wrong? 300 divided by 2. What am I talking about? 150. Does that feel better? That looks better. Okay, 150 what? Newton seconds. Cool. Okay, this last one. We are not going to go into the calcu thing. I don't think we can get an exact answer. I know we can't. Totally may be able to. If you guys want to find exactly this quadratic, we can find the actual impulse here. You guys want to do a little modeling with quadratics right now? Do you really? I'm cool with it. Gosh. Okay. Buckle up. Where's the vertex, seemingly? Top. I agree with that. Can you give me a coordinate? In brown is up to you, but it is a good skill just to make sure that we have, because you do use this. I like that one more. I wish it were 10-4, good buddy, but I think it's probably 2.5, 10. Everybody cool with that? Okay. Gosh. If only I had a way to think about a quadratic only in terms of its vertex. Like if there were some form that depended on its vertex, might become a standard way to think about graphing. There's a standard form of quadratics. Big moment here. We haven't seen it since chapter 1 in algebra or pre-calc. What is it? I know that they can look like this, and this is common. Ax squared plus bx plus c. But that's not a nice way to graph them. We do some fancy completing the square stuff, and we get something that looks like this. Cool. Okay. At this point, I am going to defer to you guys, because no matter how badly I would like us to find the exact equation of this parabola and make totally get us the area, this is not your pre-calc class. Okay. Could you guys do this? What's HK in this situation? 2.5 is H and K is 10. Okay, so check it out. For one bonus, you know what? I'll just tell you. I'm not even going to write it down. You bring this to me later. Before class tomorrow, I'll give you a late homework pass. Cool. Find me this quadratic. Now, with that in mind, if somebody finds it, I'm cool with it. But if we want to estimate the area, how would you even go about it? Like, we're not going to get a nice, perfect answer yet. How would we think about it? Can you tell me what it's at least less than? How do you know that? Yeah, so all that we can say for certain right here is that delta P is less than 50. We can't really get it. Now, totally, I'll find that equation as well, and then we'll ask the calculator or ask you to integrate it and figure out what it is. But this is as much as we can get from this idea right now. If we had a way to calculate this area, we could, and totally has a way to do it. You don't yet. Cool. Is it hard to find impulse from a graph? Pretty doable, I hope. Okay, so turns out that if force is constant or it's not curved like we see here, it doesn't vary, then this is a piece of cake. Whether it's a flat line or a straight line is nice. The second we get into curves, we get a little bit more trouble. Okay, now turns out that this applies to your everyday life, and we're going to do an example with a car. And how fast your momentum changes, which remember that's mass times your velocity, it shows up in a lot of different places. So we save lives with the understanding of impulse momentum. Like, it happens everywhere since the 60s. When you get in your car, because we're all perfectly safe drivers, I know that you check your mirrors, right? You've already checked your oil and your tire pressure and all those things. You turn on your car, but before you put her in gear, you do something else to save your life, conceivably. You put on your seatbelt, I hope. I am not the police. How many of you guys actually buckle up every time you drive your cars in town? Good on you guys. Good on you. 30 miles per hour seems like it's not enough to cause damage. Oh, it's so enough to cause damage. I don't always. But it's, yeah, mine doesn't because I have it clicked behind me. Yeah, bad habit. Don't do that. Okay, so check it out. Turns out I want to look at what causes changes in momentum. So we're going to think about a car crash real quick. If we had a car crash, we could have a large change in momentum, because if we're going really fast and then we end really slow, like stopped, then there must be a change in momentum. Okay, it can happen two ways. We can make large changes in momentum nice or terrible. Really, either situation. Okay, one option, you have a seatbelt. You have a large force over a little bit of time, or times a little bit of time. So if I slam on a seatbelt like I'm here, and I come to a pretty sudden stop. Big force over big time. Okay, compare that with an airbag, which I know it doesn't seem like it, but if you have an airbag, the collision and your coming to a stop takes significantly longer. That's what airbags do. They absorb it so that you don't go to a sudden stop, even with the seatbelt, which means you have a smaller force, but it takes more time, right? Those can give me the same number. 10 times 5, if we have 10 force in 5 seconds, that's 50. That's the same thing as 5 force times 10 seconds. The same impulse, different situations. Okay, so one quick idea, or one example, and then we may have a couple down minutes today, because I can feel that we're getting back into the swing. Do you guys have, well, we'll talk. We'll get there. Okay, so here we go. We have a 2,200 kilogram car. Okay, this thing with a velocity of 26 meters per second stops in one of three ways. Okay. So we have a car traveling at 26 meters per second, and there's three ways that this car can stop. And we could write a whole flowery paragraph saying we're approaching a red light, blah, blah, blah. It doesn't matter. Okay, so check it out. I can stop really nicely, which if I'm aware that I'm going to come to a stop, I'm going to gently depress the brake pedal. I'm going to slow down consistently, right? I don't want to slam on the brakes necessarily. So here we go. Slow brake. In, and let's say it takes, if we go slow brakes, 21 seconds. So, cool. 21 seconds to go from 26 to 0. We're going to stop. Okay. Alternatively, you could be, I don't know, distracted, singing a song, rubbernecking, whatever you want to call it. You could slow brake nicely or slam brake. Or brakes, rather. Okay. Let's say we slam on the brakes and we come to a stop in, instead, 3.1 seconds. Way faster change. Cool. What's the third alternative? You're going to slam into the car in front of you or something, the wall, it doesn't matter what it is. Okay, or crash. And in this situation, let's say that it stops you in 0.22 seconds. Okay. What I want us to do from this situation, for each of these, I want us to find the average force that the car must undergo, or the person in the car, if you'd rather. The person's not going to weigh 2,200 kilograms, so we're just looking at the car right now. All right, how much force must be used to stop this? Now, it's been a while, so we're going to start this together. We'll do one part as a whole class, and I think I'll give you guys a little time to do the other two parts. Okay, when we're setting up a physics problem, I always require you to do very specific kind of system. What's the first thing we always begin with? The knowns. So, check it out. I'm going to I want a bunch of people, because it's been so long since we've done this sort of thing. I want a bunch of people to help me out here. So, I'm going to write down some knowns. Number 13. What's one thing that we do know about this? Okay, so the car weighs 2,200 kilograms. How do I write that down as my known? Love it. M equals 2,200. And because it's mass M, we have kilograms. Cool. Doable. How about anything else that I know? Number 2. Okay, so which velocity? Because I know that I only gave you one, but what are we doing with this car? We're stopping. So when I finally stop at the very end, my velocity winds up being 0, which means this one is really the what? Good. Initial velocity. And I know it's 26 meters per second. Okay. We just spoke about it, so I'm not going to call on anybody. Just kidding. Number 1, final velocity? 0. Sorry, I thought it was writing weird. 0 meters per second. Awesome. Anything else that we need? I think so. Why acceleration? Just out of curiosity. So you could do acceleration. You could find delta V over delta T and get it that way, but we're going to use impulse momentum to make sense of this. So I'm going to have some different pieces. I need some times, I think. Okay, so for this, I will probably just use T rather than delta T when I actually write these, but to get practice with it, let's make sense. Okay, I have 3 different times because there's 3 different scenarios. We can either label these times 1, 2, and 3 and just call them T1, T2, T3, or we could just use subscript with words. I'm going to use subscript. Okay, let's say delta T for a slow stop. Kalisha, how long does it take me if I gently push on the brakes to stop? Okay, confidently shouts 21 seconds, I think is what I read your lips. Is that true? Awesome. Give me another one, Barsega. Okay, delta T, and what do you want to call this one? Slam. I'm fine with that. Is 3.1 seconds. And totally the last one, delta T, what? Crash. Love it. I mean, not crashes, but. And how much? 0.22 seconds. Okay, we have all of our known information highlighted. What are we actually trying to find? I'm trying to find the average force. Now, as we look at this, I'm looking for the force in 3 situations because we have 3 different times. We need force slow, we need force slam, and we need force crash. Okay. Now, Nick, I want to highlight, I really liked your idea, just so you know. We could calculate out the acceleration and just do it that way. But we're going to make sure that we connect this with momentum, and we'll get bigger connections with this. So, I need an equation that somehow relates all this stuff using impulse and momentum. So, equations and work stuff. Well, gosh, I'm looking for a force, and I have a bunch of momentums and all that are calculatable here. What's that impulse momentum theorem? It says force times time is equal to I could say final momentum minus initial momentum, but I didn't list either of those. How should I write it instead? So M is what I'm going to use first, and then delta V. Everybody cool with that? Okay. If I skip one step and say it's M VF minus VI, anybody opposed? And can you tell what I've done, rather? Okay, if somebody's looking, because I see people checking notes and stuff, I'm cool with it. I'll write this first. Just so it looks the same. Delta rho is what we wrote first, right? Okay, which means F delta T is, what's this idea? How do you find delta rho? Or change in momentum? So rho F, my final momentum minus my initial momentum. And I would not really do it every step this way, but I just want to make sure these ideas, again, just click. That's mass VF minus mass VI. And I'm okay to stop there. I would factor out the M if I were actually doing it, but I'm okay with this. All right, last little thing. We're trying to find the force. How do I make it so it's just force on the left? Perfect. I'm going to divide by delta T, and I lied to you guys a second ago. I am going to factor this M out, so I don't have to write it as much. Not as much stuff to plug in. We get M times final velocity minus initial velocity all over delta T. Now, we haven't plugged in any numbers, which is super awesome because we now have just a way to plug and chug through this. I want you guys using calculators, and we might start using our new less fancy calculators. If everybody doesn't have them, I'll grab those real quick. I'm going to pause it. I want you guys to find me the force that the car undergoes when we slow brake, the force that happens when we slam on the brakes, and the force of the crash when we come to a sudden stop. And just to check, I have negative 2,700 is what I have, but I'm sure your number's closer. Or is it exact? Negative 2723. Okay, and what is my unit? So careful. Why not Newton seconds? It's just force, which means it should be newtons. Cool. Why negative? Yeah, it's the opposite direction, right? Might have a decrease. Cool. All right. What about slamming? I have about 15,000. I don't know the real number. Are you guys cool with that? Or it's 18? I have a typo. I'm going to do negative 1.8 times 10 to the negative 4, or 10 to the 4. That's 18,000. Cool. All right, what if we crash? Like Sean. 260,000 or 26,000? 10 to the 5? Or 6? 5. Cool. All right. Now, this should not come as a surprise, but do you guys agree you're going to feel way more force if you slant, like you crash into a wall? You're obviously going to feel more force, right? Because it has to stop faster. This idea is what's used inside of cars. Like, they test these, they measure them. Thankfully, they do this. Airbags reduce this a ton. Cool. So, tomorrow, we will continue working on these. We get like 60 seconds to just kind of chill out.